Welcome to Electronics Specify Insights, the podcast for electronics engineers. I'm your host, Paige West. In today's episode, we delve into the evolving role of artificial intelligence at the industrial edge. Joining me is Ted Kao, AI Product Marketing Director, and Davis Sawyer, AI Product Marketing Manager at NXP Semiconductor. Together, we explore how NXP defines the industrial edge, the technical and environmental challenges engineers face when deploying AI and machine learning models in industrial environments, and how performance, power constraints, and legacy protocols are being addressed. I hope you enjoy this episode. Let's get started. Today, I'm pleased to be joined by Ted Kao, who is the AI Product Marketing Director, and Davis Sawyer, who is AI Product Marketing Manager, NXP Semiconductors. So thanks both very much for joining us. But before we deep dive into our topic of the day, I'll just give you guys a couple of minutes each to introduce yourselves. Ted, why don't we start with you?
Sure. Yeah. Thanks. Thanks for having us. So, my name is Ted Kao. I joined NXP in 2024. I spent my career in product management and marketing with a strong focus on emerging technologies. I entered the AI space about 10 years ago during the rise of the voice assistants like the Amazon Alexa, Google Assistant. And since then, my work has centered around bringing intuitive human-machine interface and edge AI to processors and driving development and go-to-market strategies.
I'll go next. Pleasure to be here. Thank you, Paige. My name is Davis Sawyer. I'm AI Product Marketing Manager here at NXP. I joined just after Ted, actually, in 2024. And it's been an exciting time at NXP since. Prior to that, I was co-founder and chief product officer at a startup called Deeplight that focused on how to make AI models smaller. Interestingly, that company was actually acquired by STMicro earlier this year. It's been definitely an incredible journey and to witness all the progress that's been made on the AI model side, and then how it actually comes into daily life or the real world through products like semiconductors, smart sensors, and more. I also sit as a co-chair on the Edge AI Foundation, which is a nonprofit based in the Bay Area, as part of their Industry Blueprints work group, where we do live streams and we showcase real world solutions to real world problems. I'm happy to be here.
Brilliant. Thank you very much. And I'm sure most of our listeners will be familiar with NXP as a company, but why don't you give us a brief overview as to who NXP is and what you guys do?
Sure. Yeah, happy to do that. So NXP is a semiconductor provider that designs and manufactures chips for automotive, industrial, IoT, mobile, communication infrastructure markets. And we offer a wide range of silicon, software, and enabling tools that empowers devices to sense, think, connect, and act intelligently. Both Davis and I work in a secure connected edge business line where we focus on bringing suitable AI acceleration IPs, as well as our EIQ, NXP's brand for AI machine learning development environment, to support and expedite the edge AI development.
Excellent. Thank you very much. That's a great start. And I'm looking forward to our topic today, which is going to be around industrial edge. And I'd like to start by asking you how NXP defines the industrial edge and really what differentiates it from other edge computing segments like automotive or consumer, for example.
Yeah, I can take this one. That's a great question. So the industrial edge is an emerging and very rich area of edge computing that has deep roots in technology and innovation itself. But due to a few factors, and we'll talk, I guess, in this differentiation, also the definition, how we separate it from, of course, automotive or consumer electronics. So, firstly, as most of us know, the planning and release of things like consumer electronics, like a smartphone or a TV, they typically follow, annual or biannual launch schedules anchored around, key buying seasons and consumer behaviors like winter or back to school. Of course, automotive is a little bit different, has longer planning and buying cycles. NXP is a major incumbent in the automotive business sector. And so as Ted mentioned, we actually sit in what's called the secure connected edge, which does loop in the industrial edge as a key part of our focus and industrial IoT strategy. But in these industrial settings like factories or manufacturing, and industrial sensors and IoT, they often need semiconductors or the sensor products to be in the field for decades versus a few years. So already that longevity is a major difference from what you'd see in other segments like consumer, of course. Additionally, there's a vast diversity of use cases. So although when it comes to AI, within edge computing, we might have vision, audio or text as different data modalities. What they're used for in industrial can be broadly different despite needing to run on the same compute platforms. And so that heterogeneity of use cases and sometimes extreme operating environments, that makes the industrial edge different. And that in turn has implications on the kinds of edge compute and processing that's required.
Brilliant. So, given both of your knowledge and your time spent in the industry, what would you say are the main technical challenges that engineers face when deploying AI or machine learning models in industrial environments?
Yeah, I mean that's another great question, and let me take that first. So I think there are many different challenges we have heard, and I mean deploying AI on MCUs versus apps processors are slightly different. So let me start by focusing a little bit more on like the challenges I've heard from people that's trying to deploy an AI on MCUs. And I would say that there are three primary challenges, in my opinion. I think first one is you really have to understand the constraint provided by the MCUs, which again is well known to be with a limited compute and memory. And the second one is you really have to understand the problem. I think AI is now a buzzword. Everybody imagine that AI is like magic, but really, when you are trying to dive into AI, you really have to understand what exactly is AI providing and the benefit bringing to your product. And that's when you have to take, again, latency, accuracy, robustness, and generalization into consideration. Make sure that when you do the design, those can, the AI models can really fit into the MCUs. And I think the third one is just how to get started. And again, it's really about data science. So making sure that you understand how to collect data properly, how do you prepare them, apply what type of processing is required, how do you make sure that the, the data quality is sufficient for proper training and things like that. I think that's also really important. And obviously, without the proper expectation and the right tools, it's going to be really difficult to get AI development started.
Hmm.
Do you have anything else you'd like to
No,
add?
those are great points, and it is a good question to unpack because Ted, you focus on the MCU side. I'll try to add a bit of color on what we see with MPUs and AI integration at that side of the industrial edge. And I think the first and foremost challenge or technical, barrier is really the integration integration with existing or legacy systems, for example. So you might be working in a power plant that has, analog, maybe not vacuum tubes, but analog devices and switches that have limited connectivity. So you're already, let's say, you're a bit handicapped in terms of the data collection or the connectivity environments that would beget, a data science problem, as Ted was alluding to. So that's on one end of the spectrum, that legacy system integration. Then you need to think about, because of the longevity required, how do you future-proof your AI horsepower by estimating, okay, maybe what today's workloads look like, but then trying to predict or speculate or estimate as best you can what might be coming in the future so that you're prepared for that as it comes out, because as we've seen, doubtlessly AI models advance, at a very rapid pace. And so, for example, in this case, you could add a discrete NPU or capacity for a discrete NPU for the added compute as one example. And lastly, I'll round it out with some AI specific challenges for industrial edge that really start with the model versioning and updates. So let's say you have connectivity, you've integrated with the legacy system, you've gotten over those barriers. Well, now how do you keep this system, updated and maintained in production? And so this is where I think we found some unique ways to approach it actually from NXP's own tooling, such as with ways to fine tune an LLM with a process documentation like a PDF, for example. That's something a human operator could do with a machine in the field without needing technical or programming experience. And so I think these kinds of thought process and exercises really, really help actually, create real world solutions that survive.
So, what constraints do industrial edge devices face when it comes to power and memory and compute, and how are those being tackled?
Yeah, I mean, I think to address those, we'll look into both from, I mean, hardware and software perspective on how NXP address those challenges. So, I mean, first of all, I mean, let me start with, again, focusing a little bit more on microcontroller side. So, I mean, we provide a wide range of microcontrollers that's designed to meet the different compute, memory, and power consumption needs. So we have MCXN for high performance, MCXA for general purpose applications, MCXL for low power, and we also have RT crossover family that combines the simplicity and low latency benefit from the MCU with the performance of the app processors. And higher performing devices also come with like the neural processors, the DSP or GPU for hardware acceleration, especially for complex AI inferencing. And I mean, to your question specifically for like industrial applications, we actually recently just introduced MCXE in July this year. And that's a new family of MCU products that offer robust 5-volt operations with integrated functional safety and industrial grade memory that's designed for harsh environments and with enhanced safety and edge lock to go security. I mean, all that to address the industrial applications. And that's on the hardware side by itself. Again, with a range of different compute, different memory footprint, and different designs to meet the industrial requirements. And on the other hand, besides the hardware, we also have powerful tools for AI enablement, and that takes the MCU compute and memory constraints into consideration. And for example, as I mentioned, we have the EIQ toolkit, and Time Series Studio is one of the tools that we introduced in 2024. And that's an end-to-end development tool featuring the integrated automatic machine learning workflow, or some people just call it AutoML. And this is a tool that's designed for both experienced developers as well as the people that are new to AI, and they're interested in building models for like anomaly detection, classifications, and regression. And with AutoML, developers can specify the device and the memory footprint and the limitation before the training even begins. And then the tool with AutoML can search through the different combination of signal processing and model architecture to generate models that meet the accuracy and memory requirements. And with a combination of robust hardware and the necessary software tools, I mean, our goal is really to reduce the development time and lower the entry barrier for anybody that's looking to build accurate and memory optimized AI solutions and deploy NXP processors.
Yeah, and that's a great example. Time Series Studio, I think, because of that diversity of data types and use cases in industrial, the Time Series Studio on MCU and other devices as well, really speeds up that time to market. I would just add one more example to the question page, and that is, how the industrial edge often focuses on the power saving benefits of using an energy efficient NPU, neural processing unit, versus even an embedded or desktop GPU. And so with the IMX9 family or the 9.4 specifically, for example, we can provide that necessary computing to run even the latest AI workloads like a language model, like a time series model, computer vision, you name it, while only drawing a couple watts of power, depending on a few factors that power variable can change. But I think that's something that really resonates in this marketplace.
Yeah, and I'm interested to hear what either of you see as some of the most promising or high impact use cases for AI at the industrial edge that you're seeing today.
I'm happy to kick this one off. So this domain I'm going to talk about is a very emerging but exciting class of AI models that are called vision language models, or VLMs. And they're a type of generative AI model that incorporates the reasoning abilities of the LLMs we're familiar with the added benefit of using visual or multimodal input analysis. So like, text in addition to an image or video. And so this can be used to improve the safety and security where in an industrial setting, the well-being of people and machinery, is paramount. And being able to monitor that 24/7 with the detail of a vision language model is super exciting to detect hazards before they happen or as they happen, and then use agentic class of reasoning or programs to then, trigger a security response. You trigger, alert a supervisor, call the emergency services. And so NXP was actually pretty early to demonstrate what I'm talking about, this vision language model stuff at the edge as a proof of concept to industrial customers and industrial players at trade shows like CES and Embedded World in this year. And the response from the sector has been overwhelmingly positive. And so I think recognizing we have the compute to run these models and more, and recognizing the models are accurate and reliable enough to be deployed for such tasks, I'm really excited for what this means in the industrial edge.
Yeah, and actually to add to what Davis has mentioned about the vision language model, I think again anomaly detection and predictive maintenance are I think two of the really impactful use cases and popular for industrial edge. So I think in many of the industrial setting today, sensors are getting deployed to monitor the equipment or detect issues that may not be visible to human eyes. And I mean, catching them early and in real time, it can really prevent like damages or minimize the material waste or avoid costly like production downtime. So I think that's also really important. And having the sensors to monitor machinery health again 24/7 is extremely valuable. I mean, not only this can enable real-time anomaly detection, also supports again predictive maintenance and allowing the equipment service as soon as it's needed. And again, traditionally, I think the maintenance is scheduled periodically, and again, sometimes that can miss the gradual wear and tear and can be inefficient. So I think those are some of the real world use cases that are getting deployed in industrial environment today. And I think more and more people are finding that really, really beneficial.
Brilliant. Yeah, some great examples there. I'd like to focus now on some of the security risks and what some of the best practices are. But let's start with the risks. So what are some of the unique security risks when deploying AI models to the edge, particularly in industrial settings?
Yeah, I mean, let me take on that one. I think some industrial applications, I mean, they definitely generate proprietary and sensitive data. And I mean, sending those to the cloud, I mean, it does create privacy concerns. So by running AI inferencing on the edge, data processing runs locally and under secure environment is important. It helps meeting the data residency and privacy regulation by again avoiding the cloud transmission. I think that's really, really important. And we're also looking at AI that can detect anomalies and security threats, such as equipment tampering or unauthorized access. Again, I think the goal is really to detect those in real time and trigger like fast mitigation actions without waiting for, again, cloud analysis.
And what about once a model is deployed in the field? Are there any best practices you can recommend for updating and maintaining or even retraining it?
Yeah, I can tackle this one. So this is a key part of ensuring that once an edge AI powered solution is deployed, that it keeps working as intended, which does perhaps interplay with security, in a few ways. And so one of the biggest factors that influences the model accuracy over time is a concept called data drift, which in simple terms means how often does the probable distribution of the real world data inputs change and change meaningfully. And so you can think of this as like fog forming on the lens of a camera in the mornings, or seasonal changes in wildlife and the colors that you'd see in vegetation over time. And the reality is that you can never get 100% accuracy with an AI model using pre-trained data or any data. But what you can do is you can leverage software tools that are sometimes called ML ops, like what you'd have with DevOps or SecOps. ML ops is a class of software tools and systems and best practices that help you manage and even improve your AI solutions performance over time. And this uses a few things like model retraining, over-the-air updates, firmware updates, and a branch of tools called observability tools, which really do that kind of ground truth comparison of an ML model's prediction to what actually happened, and then having sometimes human in the loop feedback, depending on the type of model you're using, whether it's generative or perception model. And then you can get more sophisticated from there. That really does depend on probably the complexity of the data and application. So maybe if it's robotics, now you'd be using reinforcement learning in some cases and simply just sampling new data, retraining your model whenever it's cost effective. I think that's very true of things like time series data, where the models are lightweight. You can use AutoML. So it really comes back to what the nature of the problem is, but all those practices you mentioned are feasible at the edge thanks to these types of solutions.
Fantastic. And given all that you've both said so far, I think it's clear that we've come a long way when it comes to the capabilities of AI at the edge, and you've both given some great real world use cases. But if I can ask you to put sort of your forward thinking caps on now, how do you see AI at the edge evolving over the next, I don't know, say 2 to 5 years?
Yeah, this is always a fun one. I'll keep going, Ted, and then please please add in. So I'd put it this way, there's only one place to go from fast, and it's faster. And what I mean by that is we can expect significant improvements in AI model performance on edge SoCs, thanks to things like neural processing units and NPU acceleration, optimizations to the model like low bit precision quantization. So converting models from floating point to integer for faster, more energy efficient, cost effective arithmetic without compromising accuracy. And then, we can always expect ever better models from the AI model ecosystem and the research community, right? So in technical terms, I think, faster time to first token and tokens per second, if we're talking about transformers and Gen AI models, even surpassing human reading and listening speeds, which will enable like truly conversational AI at the edge in the near term. And then I think with sensor fusion, so maybe radar and lidar and other complex systems emerging, multimodal systems as they're often called, that will power the next generation of things like mobile robotics, autonomous UAVs, and even more in the longer term. That's my 2 cents.
And I fully agree with what Davis has mentioned. And just to add to that, I think AI in the next couple years, I mean, definitely AI is something that can be continued to get adopted, can be improved once the more and more data is generated and collected. I think the improvements in terms of accuracy is definitely going to improve. And while the hardware continue to get evolved, again, more and more people are looking for lower power, smaller memory footprint. I think those are going to be, I mean, the future of AI. How does it get adopted in the lower power, lower memory devices, as well as improving the accuracy with additional data that can be used for training.
And what about for NXP in particular? What's the company's long-term vision for AI at the edge, and where do you see the biggest areas for growth?
I can start. So I think it's the convergence of a few, we'll call them mega trends that are actually being implemented today on our silicon and future generations, of course. And that's the convergence of these Gen AI models, so LLMs, which we're doing today, the vision language models I alluded to, with the power of agentic workflows, agentic AI systems, and then that physical AI factor, because we exist at the point of data capture in more than processing, sensors, connectivity, other solutions. I think we sit in a good, the rightful place to really drive growth across all those trends, and that's in markets like the industrial edge and beyond. And one product that I'm excited about that I actually help own and drive is what's called our EIQ Gen AI Flow. And Gen AI Flow is a software tool that's kind of an out of the box, ready to go experience for domain specific, so you can customize it with your own data, like a PDF document or other sources, and contextual around the conversational interface or human machine interface at the edge. And so I think with things like Gen AI Flow running on the IMX 9 series or IMX 8 series, with the added benefits of discrete MPUs, like with NXP's Intenta Quaranara, which is a discrete MPU company, that'll all converge to make things like agentic AI, physical AI a reality. And that's a lot of growth right there.
And I fully agree with what Davis just mentioned. Again, generative AI is definitely the key. And one thing that a lot of people are also asking is, again, how do you make Gen AI small and fit into the edge devices? So there's people also talking about small language models. So instead of the large language models, making more domain specific and making sure that the model can fit onto the edge devices. Today, majority on the app processor, but hopefully in the future that can be also be deployed into the crossover type of devices or even microcontrollers. I think that would be huge. And I mean, other than that, I think again, real-time edge inferencing that doesn't rely on the cloud, doing better predictive maintenance, autonomous operation while like maintaining low power and cost efficiency. I think those are all the key area for us to invest in. And I mean, outside of the AI, or actually part of the AI, is also to further enhance the security and privacy of not just the AI, but in entire application. So those are still like the paramount of the solutions.
Excellent. So finally then, before we wrap up, is there any advice that you'd like to give to our listeners and our engineers or product teams who are just starting to explore AI and ML solutions for industrial use cases?
Sure. I mean, let me start on that one first. So I would say start by identifying what the real problem is that AI can really solve for you. And I mean, understand the pain point, understand the constraints. I think those are important just to set the right expectation and understand where you can tackle it. And I think the second one is also definitely start with the practical use cases where, again, data can be accessed and collected for preparation and for training. I think having those would definitely allow the developers to get a head start.
Yeah, I think that's a good practical recipe. And I'll add to it that we're living in a time where what seemed kind of like science fiction is now possible, not just with cloud or AI PCs, but at the edge on microprocessors, apps processors, and even MCUs. And so I would say that there's a lot that can be learned from the latest demos and reference designs from semiconductor vendors like NXP, NVIDIA, others, where that can inspire what's cutting edge and help answer those questions Ted said about what are your own tasks, what are your own constraints and challenges, and then use these reference designs to pave the way.
Excellent. Well, Ted, Davis, thank you very much for joining me both today. It's been a pleasure having you as a guest on my podcast, and I've really enjoyed learning more about NXP's solutions in this space, and in particular hearing your predictions for the future of AI at the edge. So thank you very much for your insights. I'm sure our listeners really appreciate it.
Likewise. Thank you, Paige.
Thank you. Thanks for having us.
Thank you for listening to this latest episode of Electronic Specifier Insights. Don't forget to subscribe to the series to keep up to date with our newest guests, and do share with fellow colleagues, friends and family who may be interested in the latest news from the electronics industry.